Now let's look at applications of linear systems with 3 variables. In these problems, we're going to be looking for 3 unknown quantities that we can call x, y, and z, or whatever letters we want to. It really doesn't matter what letters you use, as long as you're consistent and you know what those letters stand for. So we'll represent each unknown using a different variable, up to 3 variables. We'll write a system of 3 equations in standard form. We'll try to get rid of decimals or fractions because that'll make us solving a little bit easier to manage. Solve that system of 3 equations just like we've been doing, and then make sure we go back and answer our question and involve units in the answers. So here we have a table that shows the costs of purchasing different combinations of hamburgers, fries, and soft drinks, and we're going to do a little bit of forensic analysis to try to determine how much each of those items actually costs as an individual. So how much is the cost of a hamburger? How much does one order of fries cost? How much does one soft drink cost? We're backtracking. We've got totals, but we want to know how much the individuals are. So we'll start out, let x be the cost of a hamburger, y the cost of fries, z the cost of a soft drink, and we're going to write that system of 3 linear equations that represents the data in the table. X, y, and z are the costs of these items, cost of a hamburger, the cost of a french fry, the cost of a soft drink. So if we ordered 1 hamburger, we'd say 1 times the price of the hamburger, 2 times the price of the fries, 4 times the price of the soft drink, and that should equal $10. So that's our first equation. X plus 2y plus 4z has to equal 10. And we're going to do this for each row in the table. So 1x plus 4y plus 6z is 15. And then 0x, we usually don't put a 0x. 3y plus 2z equals 6. And that's our system of 3 variable linear equations. Now we need to solve the system. We're missing an x term in that third equation, so I'm going to take the first 2 equations and eliminate x in them in order to get my system of 2 variables. So I'm going to multiply this first equation by -1, keep the second equation as it is, and add them. X's will cancel. 2y plus 2z equals 5, and I've got 3y plus 2z equals 6. There's my linear system of 2 variables. So we've reduced the 3 variable system into a 2 variable system, and now we need to solve the 2 variable system. So I notice that my z's are the same coefficient, so I'm going to multiply the first equation by a -1, and I get y equals $1. So my fries are $1. We'll highlight that so that we can come back to it. And then continuing on, now we need to find z. So 2y plus 2z equals 5. Y is 1. Subtract 2. 2z equals 3. So z equals 3/2 or 1.5. We can make it into a decimal, that's okay. And there's our answer for z. Now we take these 2 values and plug it into either of the first 2 equations that have x's in them. I'm just going to use the first one. X plus 2y plus 4z needs to equal 10. And 4 times 1.5 will give me 6. So x plus 8 is 10. Subtract 8. X equals 2. So we have the hamburgers at $2 a piece. The fries are $1 a piece. And the soft drink is $1.50 each. Checking the reasonableness of this answer, we need to go all the way back up to the beginning. $2 plus $2 plus $6 does equal 10. So I'm just checking them. Hamburgers, 2. Number of fries is 4 times 1. So I've got 6 so far. 6 times $1.50 is 9. So I've got 6 plus 9 is 15. The second equation works out. And then 3 fries plus 2 soft drinks, 3 plus $3. 2 times 150 will give me $3. 3 plus 3 is $6. And it works out. So these numbers make sense when I compare them to what's in the table. And that's how I can check my work as far as the reasonableness of it.